Welcome back. So this is the last part of serial communications, the lecture series on serial communications. We have already covered UART and SPI in detail, and this is something which is actually very useful, and something known as integrated circuit. So it's actually I to the power of 2C. Okay, so we know that UART is an asynchronous protocol. SPI is a serial protocol, and there are quite a lot of differences, right? UART ideally requires only one wire for transmission because there's no clock line, and SPI, for example, requires 4 wires, right? One for clock, one for transmit, one for receive, and then one for the slave select. And we understood in general how is the process for configuring something for SPI or something for. In this section, we will be spending time on another synchronous serial communication protocol, which is I2C. And I2C is invented or popularized by Philips Semiconductors. It was that time Philips Semiconductor, and now it is commonly known as NXP. If you see somewhere NXP, please do remember that it was started by Philips. Then previously we saw UART is sort of one-to-one communication, right? There is one master and one slave, that's all. The reverse communication is not possible, so it was simple. Then we realized SPI is much more useful, where you have multiple slaves and a single master. And then it is possible to have slave to master communication also, but it should be initiated by the master by issuing a read command, right? That's the thing. Now here is a protocol which can have multiple masters, okay? So that's interesting, and of course multiple slaves. And previously, if you remember, in the case of SPI, we have a slave select wire, and if we have a new slave, we need to have a new slave select wire, right? So let's say I have 7 slaves, then I need to have 7 separate slave select wire. So that's the complexity addition for that. But having said that, I have a slide on comparison of these 3 protocols. There we will discuss and compare amongst each other, but let's concentrate on I2C only for this section. Okay, so typically the speeds are not compared so far, but we will see that this is one of the fastest protocols, and it is possible to even communicate with low speed peripherals using I2C. Okay, and then this is the most interesting aspect. So we have typically I2C, when they say these 7-bit or 10-bit addressing schemes. So let's say it's 7-bit. Okay. So if it is 7-bit addressing scheme, then I have 2 raised to 7 locations possible, or that means I can have 2 raised to 7, that is 128 I2C slaves possible. That is amazing, because when we started with UART, it was just 1-to-1. USB is an advanced UART where you can typically consider that as a single 1-to-1 communication. Otherwise, you put a USB hub, again, it is sort of daisy chain, right? Daisy chain. That's a way to get out of that 1-to-1 in the case of USB. But typically it is 1-to-1. Then we went to SPI. You can have multiple slaves, but for each slave, I need a slave select wire. That is tedious. And here is an option where you have 7-bit addressing possible, which has a capability of adding 128 slaves. And if you have 10-bit, 2 raised to 10, that means 1024 slaves can be connected to a master, and that is amazing. That is why this is one of the most popular serial communication protocol available. For example, in our freedom board, we have a 3-axis accelerometer, x-axis, y-axis, z-axis. I briefly showed one application where we tilt the board and you see the variation in the RGB LED color, right? So remember there you have 3 accelerometers, one for X, one for Y, and one for Z, right? So then this is interesting to see that it's quite easy to interface that with an I2C. So in fact, our accelerometer is connected to the microprocessor through I2C protocol in the case of freedom board, and most of the times as well. Okay, so that's important. Keep in mind, most of the time we'll have 7-bit addressing scheme. So 128 I2C slaves are possible, and 10-bit addressing scheme, if it is there, means 1024 possibilities are. And amazingly, you might think that then you need a 7-bit or 7-wire line. No, that's not the case. You only need 2 signal lines, one for clock, one for data, and that's the key. So in the data line itself, you will send the address of the slave that you're looking for. So that's the most important aspect. So we started off with UART, which has only 1 wire, ideally. Then we went on to SPI, which has for 1 slave, it has 4 wires. And now here is a system, which is I2C, where it has only 2 wires, but there is a possibility of 128 slaves or 1024 slaves using these 2 wires. Okay. So it is something like this, if you want to put in a pictorial way, where engineers like this way. So you have a master, most probably it will be a microcontroller. And then it has 2 lines, one for data, SDA, and the other for clock, SCL. S stands for serial. So serial data, serial clock, that's the meaning of it. And each one of these is connected to each of the slaves. So here I have shown only 3, but for a 7-bit scheme, this can be like up to 128 slaves. Okay. So this is typically how for an electrical engineer it looks like. The previous one is more for a computer science electrical electronics mixer. But for an electronics electrical engineer, it looks like something like this. And I think this is common for UART also. When I said, if you remember, UART line is always, the data line is always high, right? So I mentioned that. How is that possible? It's something like this. There are some resistors which are pulling it up to VCC all the time. Unless it is driven to ground, it will be always at high state, okay? So that's what the meaning of it is. So here, for example, both clock and serial, you can pull it down to ground using these options. Okay. This is the output part, and this is the input side. So it's a tri-state buffer sort of scenario. Okay. Okay, so you have to give, let's say you're putting it 0 here, then the pull up is already done. So it will be going like this to the ground, and otherwise it will be high state. So no things possible for the buffer. So the clock, there are many possibilities, like we control the baud rate in UART and then in SPI. Similarly, here also you can control the clock frequency. Clock division is possible. That's what I'm saying. Going forward, so this is a maybe somebody is very interested in a more detailed fashion. Because of this high value of pull-up resistor, the speed of I2C is actually reduced. Okay, so otherwise we could go beyond this 5 megahertz, but typically because of these resistors corresponding dynamic power loss, it's restricted to this range typically. You can ignore it and nothing much there, but somebody is very interested. It's just a fine line of detail. Okay, so coming back to now, how does it work? So I said I can connect 2 raised to 7 devices, right? But how is it possible? So let's say this is the master here. So I would like to call it primary, secondary, rather than master slave. But if somebody is keen, this is the master, this is a slave. So how does I2C protocol typically works? The first step, the foremost step is to issue this, okay? You have a start, basically I2C start, plus the 7-bit address that I'm interested in, okay? So let's say I have 128 devices. The first device obviously will have the address 0x0, right? I mean 0x0 in the sense like 00, whatever, okay? Then we have to mention also whether I want to read or write. That's also important, right? Whether this guy wants to read from the slave or secondary device or write to the secondary device. Also, this is, so in this case, I'm just illustrating it using a write operation. Okay, so this is first. So it is like I'm starting the transmission, and first I will transmit the 7-bit address, and then we'll issue that I want to write to this address. Okay, so that is the meaning of this. Then you wait for an acknowledgement. Okay, so this is important. So it's slightly different from SPI. Okay. So here you will wait for acknowledgement, and just to ensure that the address you send is good. Okay, so if it is not good, that means you send something wrong. So you wait for acknowledgement. Once the acknowledgement is good, then you send again the data. Okay, so I will show in the next slide slightly different picture, where sometimes, for example, in our case, we have the 3-axis accelerometer, right? So there are two addresses there. One is the device address, which will point to the accelerometer. And then there is another address, which is pointing to x-axis, y-axis, or z-axis. So then in that case, I need to send two addresses. So instead of data, I will send the address again. That will point to, let's say, x-axis is what I want to write, or y-axis is what I want to write, okay? So in this case, I'm just illustrating that there is only one address, which is the device address. And once address is acknowledged, then I will send the data to be written to that particular device. Okay, so that's the thing. Again, I will wait, but the data is received nicely intact. So I receive the acknowledgement. Moment I receive it, I will send, okay. Again, something like stop, I will stop the data, stop the transmission. So that the slave is relieved now, and it can go for another transmission. So that's the meaning of it. So it is a very, very nice handshaking way of, it's a something which is in between a synchronized and asynchronized, or handshaking, hand synchronous, or with the presence of clocks. So this is an example where I'm sending a device address and then an internal register address. So you can think of something like the accelerometer address here, and then maybe the x-axis address here, and then the corresponding data. So this is the way we do it. So we have a start bit plus the data. Okay. Remember here it's a 7-bit address in this case. So if it is a 10-bit address, we'll have A0 to A9 here. So here it's a 7-bit address. I will put the 7-bit address plus I specify I want to read or write. Okay, so that's important aspect. So once I do that, I wait for the acknowledgement. Okay, so this is something like how the SDA line will switch. Okay. So for each clock line, I'll have MSB, then so on. Okay, so something like this we'll have, and then read write I will have, and then acknowledgement. Then I will send the 8-bit internal register address. Okay, so this is something which is not like the slave address, but within the slave, if I have multiple addresses or multiple registers to read, I will do this way. Okay? For example, the x-axis in our accelerometer. So this is also gone, and then I will again wait for acknowledgement, and then I will actually write or read the data, whichever way I put here. Right? If I read, this is the data I will read. If I write, this is the data I will write. Okay? And then again, finally, we'll wait for the acknowledgement. Data is also fine. Then we'll issue the stop bit. And remember, as I said in this case, it is always put as high. So the ideal state is always high. If you see here SDA, the normal state is always high, and the operation is done, and again it goes back to the high state. So that's the key aspect. Okay, so start is always issuing a high to low signal. Similarly, clock also is similar. That's why I'm sorry to go back again to mislead you. So both are actually tied up to high state. You can see over here. The same scenario is there for the UART also. Okay, so this is the way it goes. So basically, we need to have a start bit, the address bit, the device address I'm saying, then the read write option. You send it over. Wait for the acknowledgement. Acknowledgement done. You send the internal register address if it exists. If it is not there, it's not needed. Again, you wait for the acknowledgement. You send the data, or you wait for the data to arrive. Again, you wait for the acknowledgement. Okay? Then you issue the stop bit. Communication stop. So it's slightly complicated compared to SPI or compared to UART, but it's a very, very popular tool because of that extreme possibility. Now this is how for a freedom board it looks like. Okay, so this is the internal circuitry, for example, and this is the address part, and this is the data part, and these are the bunch of registers I will be interested in, and then the start, stop, data, that manipulation part, the in-out register part also. So data will shift in and out from the register here, and then this is how the communication happens to the other device, SCL, SDA. Okay, so this part is already done. Please go through the manual to understand it in more details. So we'll go through that in a bit. And two I2C devices are there in our freedom mode: I2C0 and I2C1. In fact, I2C0 is connected to the accelerometer in our case. Okay. So now let me just quickly go to the manual so that you are well trained in that. So again, go back to this and go to the about I2C. So this is a chapter about, please go through in detail. Now it's like, I don't want to spoon feed everything. Most of the details are self-understandable now. So if you have any issues, always come back. The diagram I was talking about. This is a set of registers that we have. Okay. So I'll just quickly go through some of them. This is the I2C register for A0. In fact, both of them are same. So the basically the 7-bit address, this is not used. Okay, and then frequency divider, this is where you can actually regulate the clock. Okay, so you can actually go for some formula here which is mentioned here, and correspondingly you put the value, you will get the data, clock frequency. Then this is something which is more important. So I2C control register, everything is important. So you have to obviously enable the I2C to make it useful. If you want to enable interrupt, that option is there. Then it's master slave. So most probably for microcontroller, this will be always master. Then in the transmit mode, if it is you want to read or write, so correspondingly this has to be set. If it is write, obviously this is to be transmit. And if it is read, it has to be receive. And then you have acknowledgement. Okay, so just enable this if you want to enable the acknowledgement option. Okay, so that's the thing. Then RSTAA is the receive acknowledgement, which I think so. Let's read it out. No, sorry, repeat start. Okay, sorry for that. So, and then these two, DMA and wake up enable. So low power operation, for example, you can disable this and wake up whenever some data comes or when this data register becomes full. And then status registers is also important. I think this is where we have the whatever the status, the receive acknowledge, for example, all the status for the register. And then our friend, the data. Okay. So that's it. So this is for the control register 2. So here also you have some options. So I suggest you read through it to understand the capabilities of your board and capabilities that you have in hand. And I have a small example also here. For example, this is a code for setting up the I2C. So if you go to the startup module, so some of them is already basically reserved or made for you. For example, if you want to start the master mode, you want to write to this control register 1 some value. So this value is already defined for you. Okay, so this is already explained here. So indicate start, otherwise stop. So that's what it is doing. And this is same register. So you can see this is not of this operation. So that means it is opposite of it, and it is to stop. And this is to make repeat start. Okay, so these three are done using C1 register. And again, transmit enable, receive enable, we already talked about it. Then acknowledgement, just wait for acknowledgement till that time. It's like busy. So your base busy, I2 base is busy waiting for acknowledgement. And this one is to ensure transmission is complete. So this is like you check the status register to see the data register is empty or not. And then some options to wait also. Then acknowledgement not received, acknowledgement received, and all these options. And then I'm not going to go in detail of all these. I just want to show you. So this is to enable the clock to the I2C register. And this is to enable the corresponding I2C pin, basically pin clock as well. So for example, in our case, if I go back to the case here, for example, the this one is the accelerometer is connected to pin number 24, 25, or 40. So we obviously have to enable the clock to the 40 to use that, right? So that is what I'm doing here. And then this 40 is obviously multiplexed. So I select the correct input so that it is actually. So if you go here, I think I just show you something. So This is where it is defined inside this header file, okay, startup file. So it's all defined for you. So of X is what you will be worried about. So if you put 5, it means it will generate 101, and then corresponding pin will be multiplexed to the option that you choose. So in this case, it is accelerometer option that I'm choosing for for pin number 24 and 25 of port B. Okay. And this is where I'm setting the speed of clock, and then of course I'm enabling the I2C and setting it to master mode. Once I do this, I'm ready to transmit something, and then you do typically, let's for example to write, maybe I'll start with the write operation. Okay, so I'll do the I2C start. I2C start is nothing but these two, transmit and send the start bit. Okay, so that is the thing. So you enable the transmit mode of I2C, you send the start bit. Okay? That's what it does. And then you send the address. Okay, so I'll just put this one side by side so that you understand what I say. So this is what the start and the 7-bit address. So this will start, and then this will send the 7-bit address, and of course that will have the read-write option also. And moment you have it, you wait for the acknowledgement. Okay, so that's what it does. And then I send the address. So this is the device, sorry, this is the device address, and this is the address of the register if it exists. Okay, otherwise you can ignore these two steps. Again, I wait for the acknowledgement, and then there is an option to have a repeated start. So this is like I will, this is to ensure that I write it correctly many times. Okay, so that's the thing. Oh, sorry, this is read. I'm sorry for that. This is repeated read operation. So start, device address, wait, the internal register address, wait, then you send the data, wait. Once you receive the acknowledgement, you stop. So write is very, very simple. And read is also simple. So this is a read byte. I will not put that. So that's something slightly complicated. Read, I2C start, then the device address, wait, the internal register address, wait, then you do the repeat, the read. Basically repeated read is nothing but if I go back and see, it is, what is that? Yeah, the restart is something like I repeat the start, okay, till I send all my data. And then this is where I'm sending the data to, and then waits. And then what is I2C receive is if you want to receive something. Okay, so that's the, basically you want to receive the data. So start, device address, acknowledgement, internal register address, acknowledgement. You ensure that the data, the registry is set, okay, and then you wait, and then you start receive the data. So this is the receive. So that's it. So sort of I2C protocol is over, and the illustration is also over. And I would like to slightly deviate, okay, and show you something which is important. So if you saw here, you might have seen this tab. So Arduino, you might have used it. So Arduino also, you have the SPI.h, which is very similar, and similarly wire.h. So SPI stands for obviously SPI in Arduino, and wire stands for the I2C protocol in Arduino. So let's concentrate on SPI here. So these are the different options for the SPI you have. And this is how you typically do. And there are some examples also that you can go back and see, 2 examples. This is for your reference. So just go through this and understand. And in fact, Wikipedia's page on SPI, if you go and click there, it will explain about SPI protocol and all this. Okay. So you might have used it without understanding. So SPI begin transmission, SPI settings. This is a baud rate. MSB first or LSB first. You do that. And SPI mode. So these are different things which we never discussed in detail. So there is option to have clock, polarity, phase, whether to capture the output during edge, something like that. Okay, so these options are there. This is the way to end transmission and so on. Similarly, I2C, a lot of examples here. Okay, so have a look at it because you should not just restrict to the freedom board. You already have these options here. If you have Arduino board with you, I suggest you to play with all these options, okay, whatever we discussed so far. Okay. So that's it. It's done, everything. Now this is something which is important, because as an engineer, you have all these options in front of you. UART, SPI, I2C. So which one to choose, where all these confusions will come. Why so many, right? We already discussed on that aspect. And it is important that you actually decide, okay, so which to choose. So as we discussed, UART is one-to-one. Even though I'm showing transmit and receive separate, this will be a single line and ignore ground. So this is a very realistic representation, but it is a one line, right? And SPI, one master, multiple slaves, 4 wires in fact. So one for clock, 2 for data, and 1 for chip select or slave select, okay? And then I2C is a 2-wire system, 1 for data, 1 for clock. You can have 2 raised to 7 or 2 raised to 10 number of devices connected to it. Okay? So this will also can have 2 raised to 7, but then you need to have 2 raised to 7 chip select lines, which is definitely not feasible. Okay. Now coming to a systematic comparison, so this is one-to-one or simplex, I would say. UART. This is simplex or half duplex, because the same line can actually act as transmit and receive. Okay? SPI is fully duplex, because 1 for transmission, 1 for reception. This is asynchronous. There is no clock in UART. SPI and I2C are both synchronous, because you do have a clock. But in 3 cases, you can definitely set the rate of transmission. Okay? This is ideally 1 wire or 2 wire. If you want to consider the ground as the second wire, it's 2 wire. Otherwise, it's a 1 wire system. SPI is a 4 plus, I would say, because chip select, if you have multiple slaves, you have more than 1 wire for chip select. But ideally 4 wire system. I2C is definitely 2 wire system. No complexity there. Okay. UART typically average speed, I would say 230 kilobits per second. SPI is 25 megabits per second, and I2C is 1 megabits per second. UART acknowledgement, you can have pins for that. That's what I was telling about the flow control and all, or RTS, CTS, and all those things in an RS-232. Please go back and check. So there is an option. Both these SPI and I2C doesn't have any acknowledgement pin, but I2C works on acknowledgement. So please remember that. Okay, but uses the same data pin. Power wise, UART is medium power. SPI is your friend in terms of power consumption, and I2C is also medium power. So this is the way you should actually proceed when you decide. So you should be thorough. And most of the modern day protocols, USB, CAN, many other things that you come across in future when you dedicate yourself to this at some point of time in your engineering life, is all based on these 3 serial communication protocols. So once you are expert in this, so there is a limit to which I can cover them in the class. We will do something on UART thoroughly, but I would ask you to actually spend serious amount of time doing yourself some simple projects on any of these. Try to understand it thoroughly, and I will be always there to help you out. If you have any questions, please feel free to write your questions in the discussion forum. I have not seen any questions so far. Encourage you to highly do that. Anyway, we have scheduled a live session also. If you have any questions there, we can even discuss them also. But I suggest putting in discussion forum, because I will also have time to look into your specific question and come back to you. Okay. So thanks for coming back, and that sort of concludes the serial communications lecture. And now we will move on to the second last, I would say, which is the analog to digital conversion and digital to analog conversion. Okay. So coming back, thanks for joining today. See you at some point of time later. Thank you.